This final oceans lecture is about tides and coastlines. So we're going to start with tides. So if you've been to the coastline here in Massachusetts, you will have noticed that we have 2 high tides and 2 low tides every day. Especially in Massachusetts, you have to be extra careful because if you screw it up and you take your boat out and then it turns into low tide, you might get stranded because we have a very high tidal range here in Massachusetts. It's not the same everywhere else, and we'll talk about that here in a second. So, what causes tides? Tides are created by the pull of the sun and the moon on Earth. So, the sun has a gravitational pull, the moon has a gravitational pull, and the side of Earth that is closest to the moon at any given point in time is going to have the water. It's exaggerated here, but basically, the Earth's water, ocean water, is going to be slightly pulled towards the moon. So this creates kind of a pocket, and again, highly exaggerated pocket of water that kind of stretches out at Earth's equator, and then a lens of water that kind of gets pulled slightly closer to the moon. So as Earth is rotating, though, every day, that can kind of change the way that tides move around the globe. And then also the fact that the moon orbits around Earth on a 28-day cycle, the moon phase also affects the tides. So the moon is pulling on Earth's water. It creates this little envelope of water that gets stretched a little bit. And depending on what the phase is of the moon, that creates different types of tides, different heights of tides, which we'll talk about. So, oops, I did only have one graph here. Okay, so just looking at a traditional kind of East Coast environment, there's 2 high tides and 2 low tides every day. So basically every 8 hours, it's either high tide or low tide, high tide or low tide. It switches back and forth. So this is from Charleston, South Carolina, but as an example, this is what we call a semi-diurnal tide, which diurnal means 2 tides a day, semi-diurnal means 4 tides a day. Anyway, but on any given day, you have 2 high tides and 2 low tides every single day. Same up here in Massachusetts. So let's look at tidal forces. Let me just loop this. So the sun pulls on Earth's water, and then the moon pulls on Earth's water. So if we have Earth here, the lighter blue is supposed to show you how Earth is being pulled on by different objects that have a gravitational pull. And what you'll notice is that if you watch the tides and the stretch of the tides, when the sun and the moon are aligned in a straight line, you get the most amount of stretch of the water from the pull. If you have the moon and the sun at 90-degree angles to each other, what you'll notice is that the stretch is not as great. So what this means is that at certain times of the month, there are larger tides, and at other times of the month, there are much smaller tides. So if we're talking about tides, I want to point out that just north of us, north of Cape Cod, so if here's Cape Cod and we go up to Nova Scotia and the Bay of Fundy, they have the record of having the highest tidal range in the world. So every single day, every 8 hours, the tide can rise by 49 feet in the uppermost part of the Bay of Fundy, and then sink 49 feet, and then rise again 49 feet, and sink back down 49 feet. This is the highest tidal range in the entire world in the Bay of Fundy, just again a little bit north of here. So at low tide, there's a sea arch that people can hike out to. And then at high tide, if they have to kayak out to it because it's fully submerged with water. Same thing, if you go out during high tide and you're not back at the right time, you could be stranded. At least these ones are actually docked, but you could be stranded because the water rises about 50 feet and drops 50 feet every 8 hours. So many planets have multiple moons. So what I want you to do is kind of do a thought experiment. So imagine if Earth had a second moon on the opposite side of Earth. So that might look something like this. That's the same size as our current moon. So what would happen to the tides? Would they get bigger? Would they get smaller? Or would they stay the same? And why? All right, so that's your first quiz question. Pause and come back when you're ready. A couple other things we have to talk about are wave action and coastal processes. So we'll just first talk about how waves form in the first place, how waves behave in the open ocean, and then how they behave once they're making contacting the beach. So if you're in the open ocean, it can be calm. It doesn't always have waves that are occurring, but when there are waves, the waves are determined by the wind speed and the wind direction. So the size of the waves and the direction that the waves are going depends on the way the wind is blowing and the speed that wind is blowing. So faster wind speed, higher waves or taller waves in the open ocean. So you don't also get like breaking waves in the open ocean as well. This is just showing you what a path of a molecule of water would take as an ocean wave is traveling through a specific location. And then there's a certain point if you dive, if you go on a dive or scuba diving or something like that, if you go deep enough, you'll definitely be below what's called the wave base, and then the water's not really moving once you reach a certain depth beneath the surface of the water. So there can be some big waves in the open ocean, especially if like a hurricane is passing through and you have very strong wind speeds. The bigger the wind speed, the taller the wave. So some open ocean waves can be about 100 feet tall or so, and sometimes they're called rogue waves if it's just a single one. It could also be multiple waves. So the wavelength is just the distance between one wave and another one. That could be upwards of like 2,000 feet or so. So you could have 100-foot tall waves spaced 2,000 feet away from each other. And that might look something like this image that's playing through. So you have a map here, and this map is showing you the wave height in meters all around the globe. Just to remind you that the faster wind is blowing, the larger wind speeds tend to be. An example of this is like if you were blowing on a hot soup bowl, you can create waves. The stronger you blow onto that soup, the bigger the waves you create. Same thing in the ocean. So based on that and the map that you have here, question 2 on your quiz, where would surfers go if you wanted to ride the biggest waves on Earth based on this map? And then why do you think that they occur at the location that they occur at? Switching to near shore, so that was the open ocean. We're just going to talk very briefly about the near shore. So as soon as waves get closer to the surface, the height of the wave will increase. So the wave will get taller and then they kind of scrunch up. So if they were originally, let's say, 1,000 feet apart, they're going to get closer and closer and closer together. And that's usually due to friction. So as the wave is moving closer to the coastline gets shallower and then you form friction. So friction will push a wave up and then cause it to start to bend over. And then it will turn into a steepening, breaking wave. So kind of like this one, as a wave gets closer to the actual beach, friction on the bottom will cause it to get taller and then make it start to flop over. Okay, so to finish up here, we're just going to talk about shoreline features. So geology controls, or the rock types that you have controlled if a beach is going to be rocky or sandy. We also talked about margins. So an active margin tends to be rocky. Those are the ones that have tectonic plate boundaries nearby. And if you have a passive margin that doesn't have a plate boundary nearby, you tend to have a sandy beach. So just hypothetically, if you had a beach that looked like this, just based on a quick visual analysis, I would personally assume that there's a volcanic area nearby, there's a trench nearby because it's rocky. So there's some kind of convergent boundary that has caused this rocky coastline to form. And then if I saw a picture of a beach like this, I'm going to assume no tectonic plate boundary nearby. That's why it's flat. That's why it's sandy. So shorelines aren't stable. Shorelines are constantly moving. It can just take one nor'easter up here in Massachusetts to completely destroy a coastline. So what tends to happen is that coastlines will kind of like form curved areas, but then they'll straighten out over time. How this tends to happen is that if you have a coastal area, it'll have bays and then what are called headlands. So those are areas that jut more out into the ocean, and waves don't hit them at the same speed. So waves slow down a little bit more in a bay, and they're a little bit faster moving in a headland. So the headland starts to erode away, and it might straighten the shoreline out a little bit over time. And if that happens long enough, then you kind of get rid of the bays because the headlands erode away, and now you have a straighter shoreline. The graphic playing through on the bottom right here is showing you a shoreline from 1990. And as that eroded away, basically it kind of straightened up over time instead of having that kind of curved area to it. So if erosion happens enough, then you tend to get either features or homes are going to fall into the ocean. So this is a picture from California where we have a couple of houses that were built too close to the eroding shoreline and are about to fall into the shoreline. And this happens in Massachusetts. At least one house a year falls into the ocean from what I've seen on the news. So, what do we do if we have issues with shoreline erosion in Massachusetts? If you have the money and the funds and the fundraising, when you live on a place like Martha's Vineyard, you can raise money to move features that are at danger of being toppled into the ocean due to coastline erosion. So, back in 2015 or 2016, on Martha's Vineyard, there was a lighthouse called the Gay Head Lighthouse. That lighthouse was in danger of falling into the ocean due to shoreline erosion. So people on Martha's Vineyard basically raised money and then hired a firm, an engineering firm, to move the lighthouse. So that lighthouse was built in 1855. It had historical significance. And basically what they did is they put it up on this pulley system or a rolly system. So they kind of made like a almost railroad tracks. They hoisted up the lighthouse and then they moved it back 135 feet from the edge of the coastline. So here's a picture of it after it was moved here, but that is one option that people have to try to protect shorelines, is that they pay a lot of money to move it. And if you want to watch a YouTube video about it, you could just look up Gay Head Lighthouse on YouTube, and then you should be able to find a video of the engineering firm moving that lighthouse backwards. Okay, so coastal erosion is a problem. Here's a map here that is showing you different areas and their risk for erosion in the US. So your fourth and fifth quiz question. So what are examples of two states where it would be a bad decision to buy a beachfront property? And then what are two examples where if you want to buy beachfront property, go ahead, by all means. So you're gonna have to give two examples of each, which would be bad examples and which would be good examples to buy beachfront property. So, to finish up, the way that shorelines are protected in modern times are a couple of ways. There's seawalls that can be built. So, these are just vertical walls that have solid rock in front of them. So, the idea is that if you have these waves that are coming in, the wall just stops those waves and absorbs the energy. So, it's not eroding the land more. You can build things called breakwaters. These are parallel to the shoreline. And the idea is that they trap sand and they keep sand from eroding away. So those are parallel to the shore. If you have a groin that is perpendicular to the shore, so it's at an angle to the shore instead of parallel to it, same thing, it's just designed to trap sand. Usually what will happen though is that it's going to trap sand on one side of the groin, and then on the other side erosion happens. So you don't really gain too much by putting these in, but people like to protect their properties and have these put in. And then there's something called artificial nourishment that I want to show you. So if you're on many of the major beaches on the East Coast, they do something called artificial nourishment. And what they do is they use this thing called a dredge. This is a picture of a dredge here, and it's basically a gigantic vacuum. And they will take it out to a river or take it out to the ocean. They will vacuum sand off the bottom of the river or the bottom of the ocean, send it in a pipe, and then that pipe will distribute that sand back on to the beach. So beaches naturally erode and get moved, and artificial nourishment is a way of just pumping sand back onto the beach, then use a bulldozer, spread it out, and create a nice white sandy beach. So let me show you, there might be some noise in here. I have it turned off. Okay. So this is artificial nourishment in action. So this little vacuumy thing basically vacuums the sand off of the ocean floor. It gets put into a pipe, and then that pipe just kind of pipes that sand back onto a beach to create that nice sandy beach again. So this should pan around and then show you it kind of in action where they're pumping sand from off of the beach, bringing it back onto the shoreline. So that's artificial nourishment. Okay, so to finish up, back in the rivers and streams lectures, so 2 units ago, we discussed the difference between flood adjustment and flood prevention. So if you need to go back and remind yourself about those definitions, you might need to do that here. But what I want you to do is describe the difference between adjustment and prevention for shoreline erosion, and then provide at least one example of each. So that'll finish up for this unit here on the hydrosphere. I have a couple big picture key points here if you want to look at them. And then our fifth and final week is going to be the climate and atmosphere section of this course.